Let us discuss the similarity between gravitational forces and electric forces. So you've already seen Newton's law of gravitational force, and as given here, you've seen that. And now we have a new force when we want to study electricity called Coulomb's law. And notice how similar these forces are. The two differences are that basically for the gravitational force we have a coupling constant here we'll call big G. We've already talked about it, and there's its value in units. And for Coulomb's law we have a different coupling constant we're going to call K, and later on we might need to understand that we can express that as another fundamental constant, 1 over 4 pi epsilon naught. And that epsilon naught is known as the permittivity of free space or the permittivity of vacuum, and we will talk about that later in the week. Now, this value K, notice that it's quite different from this value. It's a lot bigger. This value, 6.67 times 10 to the minus 11 for big G, the universal gravity constant. K, the coupling constant for electricity, for electrical forces, is 8.99 times 10 to the ninth. And instead of Newton meter squared per kilogram squared, this constant is Newton meter squared over Coulomb squared. And why is that? Because instead of the force between two masses, we now have a force between two charges, Q1 and Q2. So instead of M1 and M2, we have Q1 and Q2. So that is our symbol of charge, Q. Now, what are the units of charge? They are the Coulomb. In MKS system, we're going to use MKS units solely in our study of electromagnetism. The units for charge are the Coulomb. Now, so we see that it's also an inverse square law. So it behaves in the same manner. Now, let's talk more about charge. The elementary charge, we'll give it the symbol E, little e. That's the amount of charge on an electron or proton. They are the same, they're just different in sign. The electron has a negative charge and the proton has a positive charge, but it's the same value. And in units of coulombs, the elementary charge E is about 1.602 times 10 to the minus 19 coulombs. Okay? So that's very important that you understand that. Now, so the question would be, how many electrons or protons would it take to make up a coulomb of charge? Well, if you invert that number, if you take the inverse of this, just 1 over it, you'll see that it's 6.24, whoops, and I need to fix that, times 10 to the 18. So that is the number of electrons or protons in a coulomb, okay? So let me fix that. Okay, so 1 coulomb has about 6.2 times 10 to the 18 electrons. So a coulomb is a pretty big wallop of charge. That's a pretty big charge. Now, let's look at some particles that I know you're familiar with. We got a proton and a neutron and an electron. These are the particles that make up an atom, right? The proton and neutron are located in a nucleus, and the electrons travel around the nucleus, according to the Bohr model. Okay, now the charge of the proton, as stated earlier, is plus E. The neutron is neutral, it's no charge. And the electron is a negative E. Okay, now in coulombs, of course, we've already pointed this out. For the proton, 1.602 times 10 to the minus, that should be 19 coulombs. And the electron has negative 1.602 times 10 to the minus 19 coulombs. There we go. Now, the mass, now one thing that's interesting is that the proton and electron have the same charge in magnitude, but what's strange is that the proton is about 1,836 times more massive than the electron, and no one really knows why that's the case. At least there's no accepted theory as to why that's the case. Somebody might have a good theory, but people aren't in agreement about it. But anyway, these are the masses of these particles. You'll have to use those for a lot of homework problems. So you need to know this table. You need to have it, find a table of values and have it stored somewhere convenient where you can use it. And you can see that they're on the order of, they're very small, like 1.67 times 10 to the minus 27 kilograms is the proton. The neutron's very similar. It's just slightly heavier than the proton. And then the electron is 9.11 times 10 to the minus 31 kilograms. Okay, now let's talk about the ratio. We want to kind of get an understanding of how strong these forces are relative to one another. You might be tempted to try something like this. Let's say that we have two 1 kilogram masses, so 1 kilogram and 1 kilogram, so 1 times 1, and over 1 meter. So notice that if we put a 1 here and a 1 here and a 1 here, that would give us this number. That's all that's left over, 6.67 times 10 to the minus 11 newtons. So we would have that a small force of about 7 times 10 to the minus 11 newtons. Now, if we do the same thing over here and use our fundamental units, we would have K times 1 coulomb over 1 meter squared. So that would be this number, 8.99 times 10 to the 9 newtons. So you might think, wow, the electric force is a lot bigger than the gravitational force, and it is a lot greater than the gravitational force. However, you really can't compare the forces that way because that depends on the units you're using, and those are arbitrary. So how do we compare the ratio of electric to gravitational force? Here's the way to do it. Let's pick a system such as hydrogen. That's a simple system. Okay, so consider the simple hydrogen atom in the ground state. Now, the Bohr model, which is not very accurate, it was just historically, it was the first understanding of atoms that we had. The Bohr atom would state that the electron kind of goes in an orbit about the proton. Here's the electron here going in an orbit, kind of like a planetary system, and the proton's at the center. And this distance right here can be calculated with classical physics, basically, almost. I mean, you need to assume that angular momentum is quantized. Actually, you can do that derivation with energy quantization. But anyway, that distance is 5.29 times 10 to the minus 11 meters, a very small distance. Atoms are very small. Look at that. Now, how do we calculate the ratio of electric force to gravitational force? That would be F sub E over F sub G, like I have up here. Notice F sub G and F sub G. So what we're going to do is we just plug in the formula. See that? We got electric force up here and gravitational force down here. Now notice what happens when you have a system. When you have a system, the distance cancels, right? So then we just have the ratio of coupling constants and the ratio of charge times charge over mass times mass, depending on the system here. So if you take the hydrogen atom and you put in the numbers, and you should try this because you need to get very familiar with working with these big and small numbers. These are really small numbers and these are really big numbers. So when you plug these numbers in, notice that we have, let's change the notation. We have K over G, see that? Times the charge on the proton times the charge on the electron over the mass of the proton times the mass of the electron. Now, I'm just taking the magnitude. I'm not worried about the sign of the charge here. The electron's really a negative charge. We just want to know the magnitude of this ratio. So when you plug in all the numbers, you should try it out. You'll get 2.27 times 10 to the 39th. So we see that the electric force in a proton, in a system, is about 10 to the 39 times. That we say 39 orders of magnitude. Anytime you put 10 to the power, we call that like 10 to the 1 is 1 order of magnitude, 10 to the 2 is 2 orders of magnitude. We see that it's about 10 to the 39 orders of magnitude greater than the gravitational force. So that explains why electrical forces are so much greater, and electrical forces are responsible for chemistry and for life, holding atoms and molecules together. And the solar system, gravity does hold the solar system together in the universe in a macro scale sense, but the charges they all cancel out because on a grand scale, charges, the amount of charge, it's neutral. The net charge is zero. There's just as much positive charge as there is negative charge. In fact, the total charge in the universe is constant. You can't create or destroy charge. We'll talk about that in a minute. You can on a very small time scale. Those are called fluctuations, but you cannot create for instance, let's say a negative charge is created just temporarily, then the same amount of positive charge has to be created. So charge is the amount of charge in the universe is constant, and the net charge in the universe is zero. And we say charge is quantized. Charge comes in bundles of E. You can't get fractions of E. You only get bundles of E. And there are things called quarks, and they're fractional charges, but they're not free. They're bound up in nucleons and protons and see, the electron's fundamental, but the proton and neutron are not fundamental. But the particles that make up these these nucleons, the neutron and electron, the neutron and the proton, are fractional charges. They're not free, they're bound. But anyway, so free charge only comes in bundles of E. And so we say that charge is quantized, it's discrete. Okay, I hope you're following me. Okay, now this is a bit abstract. Now, so we see that for the system hydrogen, for the simple hydrogen atom, the most abundant atom in the universe, the simplest atom, just a proton and an electron, the ratio of electric force to gravitational force is about 39 orders of magnitude. Now, let's look at an interesting system. This is sort of a virtual system. It turns out that you can that electrons and positrons. A positron is really just the same as an electron, except one thing: it's got a positive charge, and this is known as antimatter. We know this exists. It's a fact of life. There is positron. There are positrons. So there's a system that can exist for a very short amount of time called positronium. And notice that in a hydrogen atom, it looks similar to a hydrogen atom, except in a hydrogen atom, the proton is so massive, when the electron's orbiting, the proton can be considered at rest. It really does move just a little bit because the mass ratio is not infinite, but that movement is very small, and the effects of the electron mass are very small. But anyway, for positronium, the electron and positron have the exact same mass. So they orbit one another like a binary star where the stars have the same mass. They're orbiting one another. And what happens to this system is it'll spiral inward and annihilate. They will annihilate and convert to high-energy gamma rays, very high-energy gamma rays. Now, this is a very important system in quantum field theory, the best theory we have in physics. But anyway, let's look at positronium, the ratio of electric force to gravitational force. So we use the same formula, and when we plug in the charges of the electron and the positron, they're the same. They are they're both 1.6 times 10 to the minus 19, and then the masses are the same, 9.11 times 10 to the minus 31. When you plug that in, you get a slightly larger number, well, 3 orders of magnitude larger. You get 4.16 times 10 to the 42. So the ratio of the electric force to gravitational force in positronium, this virtual form of matter, is about 42 orders of magnitude. Now, that's something interesting, the kind of things that us physicists think about. Sometimes we ponder, like, where does matter come from? For that matter, where does charge come from? You know, where do these things come from? And some ideas in modern physics is that they're actually like they're sort of like manifestations of the nature of space and time. Like you can think of space-time as being twisted and bent. And these charges and masses are different manifestations of those bends and twists. But anyway, let's look at positronium as a perfect system because it's so symmetric. And pair production, those are called pairs. Let's spell production there. Pair production is like when you produce a pair of particles, and there's different ways to produce positronium. And anyway, whoops, darn, there we go. Now let's fix that. Oops, what happened here? I got a problem here. I hope that doesn't stay there. There we go. Okay, there we go. Now pair production, or positronium, is also the dominant mode of photon interaction with matter. So that's sort of a statement about something called quantum electrodynamics. But anyway, let's look at that force again. So it's, like we said earlier, it's about, I rounded it off here, 4.2 times 10 to 42. So let's look at that. Now, if you wanted to estimate the total number of fundamental particles in the universe, cosmologists have different ways of estimating what they think to be are the total number of fundamental particles in the observable universe. And these estimates range from about 10 to the 80th to 10 to the 86. That's how many particles we think are in the observable universe, somewhere in this neighborhood, 10 to the 80 to 10 to the 86. Now check this out. If we assume that the number of particles is in this neighborhood of about 10 to the 85, then, and you consider virtual particles as a large number of events, like these virtual particles are events, then we know from statistics, the simple statistics, that when you have a very large number, the uncertainty in that number is just the square root of the number. So the square root of that number, notice that that's about the same as the ratio of electric to gravitational force for positronium. So here's a Cavalier interpretation, for Cavalier for sure. One might, that kind of suggests maybe that electric electromagnetic and gravitational forces are the result of quantum fluctuations in the virtual particle numbers. So basically, pair production is fundamentally related to the fluctuations in the fabric of space-time. And then furthermore, we might think, well, maybe electricity and gravity are not fundamental forces after all. They just emerge as a consequence of quantum physics. So that's kind of a strange way of looking at physics. Actually, back in 1967, a guy named Andrei Sakharov first suggested that gravity was indeed emergent from quantum fluctuations, and it's fairly popular with a lot of physicists. I don't know how many people have ever thought that perhaps electricity also emerges, but I assume people that work in string theory and loop quantum gravity think this way. It's when they're trying to come up with what's called a unified theory of all of a theory of everything, a unified field theory for all of physics. But anyway, this is sort of a cheap way out of that. Anyway, so I hope you enjoyed this lecture. You'll be using these calculations to do some homework problems. And note that when you consider a system like 2 electrons, 2 protons, that basically the distance will cancel. That makes life nice. Those 2 D's right there cancel. See that? These 2 D's, they cancel. So all you're left with is notice that this way of looking at it, for a perfect system, if you talk about 2 electrons or 2 protons, you would just have K over G, the ratio of the charge squared to mass squared. Now, of course, if you're talking about protons, this would be the mass of the proton, not the mass of the electron. Okay, you have a nice day.